So here is one example. This part we're looking at is 70 to 90% water. What we are looking at is a hydrogel containing over 90% water. You can see it's very compliant. It's soft, it's white, but it's very robust. You can stretch it, you can do all kinds of deformation on this hydrogel. At the same time, for example, we bond a computer chip on the hydrogel. You can form a very robust interface between this engineered hydrogel and the computer chip, form this kind of interface. The hydrogel has similar physiological and mechanical properties as different tissues and the organs of the human body. The computer chip or sensors, actuators can interface with external machines to form this better, long-lasting interfaces between human body and the external machines. That is the technological platform that we are trying to develop. This is a very challenging question in mechanics and materials, how to design something that contains 90% water, over 90% water, but still extremely robust and adhesive to external engineering components. The method we develop a systematic strategy, which is still use existing biocompatible polymers, even biopolymers, still use those existing polymers, but make them into an unconventional polymer network architecture. For example, existing hydrogels, the polymer network in existing hydrogels are usually randomly cross-linked. They're randomly cross-linked like an entangled network. We try to rationally design this polymer networks in the hydrogel. For example, use nanoparticles, biocompatible nanoparticles to reinforce such a network. Use interpenetrating of different networks to form a composite. Use this different kind of strategies across length scale all the way from nanometers to millimeters. So this is a multi-scale problem as well. We develop design strategies across different length scales to design this kind of extremely robust, adhesive, and active hydrogels. Use that as a technological platform to interface human body with external machines. One interesting property of the devices based on hydrogel is they have very similar mechanical properties as human body. For example, they are almost transparent to ultrasound signals. So that if you use this device in the body, you use ultrasound for diagnosis, it will not block the information of this ultrasound diagnosis. It's transparent to ultrasound. At the same time, it's also optically transparent. You can see this hydrogel is transparent, and the water is over 99% transparent, so that you can also use optical devices to observe through these hydrogel devices.